Now let's talk about some sources of alkanes. Remember, alkanes are a chain of carbon atoms and they have all single bonds. So it's like your CH3, that's an alkane. Or you could have a substituent on here like this. So remember, alkanes are just straight straight carbon chains, all single bonds. The bonds are fully saturated if they're all single bonds. Now, most of them come from in natural gas. The majority of the alkanes are actually methane and only 5 to 10% ethane. And then the rest are just mixtures of other relatively low boiling alkanes. Chief among them are propane, butane, and 2-methylpropane. In petroleum, that that is another fuel source we use primarily. Petroleum's a very thick, viscous liquid mixture of thousands of different compounds. Most of them are hydrocarbons that formed from the decomposition of marine plants and animals, which is why it's called fossil fuels. There are things called cyclohexanes. Now, cyclohexanes just are chains that are in joined together in a circle. So that's why they're called cyclohexanes or cycloalkenes. Like here, you have your butyl group, your butane group. Instead of being butane, it's in a chain, it's in a circle, so it's cyclobutane. Here you have what would be pentane if it were straight, but because it's joined together, it's cyclopentane. Here you have cyclohexane. You name these the same. You could, if you had a chlorine right here, you'd still number them the same: 1, 2, 3, 4, 5, 6. And instead of just saying cyclohexane, you'd say 1-chloro cyclohexane. So the nomenclature is still the same process. Now, a cyclic hydrocarbon, it just contains carbon atoms joined in a ring. Cycloalkanes are cyclic hydrocarbons where all carbons of the ring are saturated, meaning they only have single bonds. And cyclohexanes or cycloalkenes are very prevalent in nature. You can have them as small as 3. So you could have cyclopentane to over 30 carbon atoms. But the most common ones are 5 and 6 membered. So cyclopentane and cyclohexane rings. Those are the most common cycloalkanes in nature. Now, the most important physical property of cycloalkanes and alkanes is their almost complete lack of polarity. So they are nonpolar. Alkanes are nonpolar compounds, and their interactions between their molecules are the very weak London dispersion forces. If they have very weak London dispersion forces, that means they have very low boiling points and melting points. So you're going to find them as gases or liquids, sometimes solids, but if they're solids, they'll melt easily. So, like I said, because of the London dispersion forces that they have that are weak, their melting and boiling points will be lower than those of almost any other type of compound of the same molecular weight. And because we know that the London dispersion forces increase with increasing molecular weight, their boiling point and melting points will increase with molecular weight as well. So if you had cyclo, well, we'll just do this for now. If we have 1, 2, 3, 4, 5, 6, 7, so if we have heptane and we have propane here, heptane would have a higher melting and boiling point because since it's bigger, it has more electrons, which have the opportunity to create more London dispersion forces, which would then create more opportunities to bond. So the bigger the chain, the bigger the molecular weight, the greater the boiling point. And you can see that here. We see the molecular weight increasing. You can see that the melting point increases and that the boiling point increases as well. I mean, this is decane's boiling point is well over 100 or well over 100 degrees Celsius. Whereas methane, which is the simplest alkane, it's as far below zero as decane is above zero. Now, when we talk about reactions that happen with alkanes, an extremely important one to us is oxidation of alkanes, which is also known as combustion. Now, the oxidation of hydrocarbons, that includes alkanes and cycloalkanes, is how we use them for energy sources. So that's where our natural gas, our liquefied petroleum gas, and our fuel oil come from, and where our power for diesel and gasoline aviation fuel comes from. We rely on this immensely. So a combustion reaction, if you remember, is a cycloalkane or a hydrocarbon of some sort, so a carbon and hydrogen. We add it to oxygen, and the products are always carbon dioxide and energy. The amount of energy released depends on the length of the chain. So you can see propane, which is 3 times larger than methane, produces a lot more energy. Now, I'm going to talk to you a little bit about chlorofluorocarbons, which for shorthand are called CFCs. Now, whenever I was younger, this was a huge deal. They were manufactured under the trade name Freon. And if your grandparents have an older fridge or freezer still, they might have Freon in that freezer. And so, because they have the Freon in that freezer, they'll have to undergo special disposal for that freezer or fridge. My mom, for example, has a freezer that is 50 years old. And I have to go help her defrost it whenever I visit. And she denied that it was over 50 until I reminded her that my grandparents had got it before they gave it to her. And I reminded her that she had it when my older sister was a toddler, or they had it whenever my older sister was a toddler. And she is, in fact, over 50 now. And she was just shocked because she had forgotten that it had been that long. So if you find an older fridge or freezer, it must be disposed of properly because of the freon in it. Now, whenever CFCs were determined to be the best for this use as refrigerants, people thought it was awesome because they're non-toxic, non-flammable, odorless, non-corrosive. And among the CFCs, the most widely used were CCl3F, which was Freon 11, and Freon 12, which is CCl2F2. Now, they were used as heat transfer agents in refrigeration systems, like I mentioned before, but because they were non-toxic, they were also used in cleaning solvents to prepare surfaces for coatings and to remove cutting oils from millings. And they also used them for propellants and aerosol sprays. The 80s was huge for hairspray, so everybody was using CFCs. But scientists started noticing a problem in the ozone layer. And they wanted to see what was causing this because the ozone layer protects us from damage from the sun's harmful rays. And they concluded that this damage was caused by the CFCs because the CFCs didn't really react here on Earth, but once they got to the stratosphere, they would react with ozone. And if they're reacting with ozone, they're damaging that protective layer. So they came up with some replacements. And instead of using hydrochlorofluorocarbons, they just used hydrofluorocarbons. And so these compounds are chemically more reactive than the CFCs. And because they're chemically more reactive, they actually react before they get to the stratosphere. So now they're reacting before they hit the ozone, which means they're not destroying the ozone anymore. And since I was a child, the ozone layer has recovered significantly. There's still a hole over Antarctica, I believe, but it has shrunk. So whenever you think about how could the ozone layer be damaged, that's why, from our use of chlorofluorocarbons. We have talked a lot about alkanes. Now let's talk about alkenes and alkynes. These are closely related to alkenes. The only difference between an alkene and alkyne is that an alkene, of course, ends in ene, E-N-E, and they have double bonds. Ethylene is the simplest alkene. Here is ethylene here. That's the simplest alkene. Alkynes are hydrocarbons that contain triple bonds, and they end in ione. So you can see the triple bond here. Acetylene, which is the common name, is the simplest alkyne. It would actually be, if you did the proper name, it'd be ethyne, but nobody uses ethyne. They call it acetylene instead, which is a little tricky because ene is reserved for alkenes. The nomenclature would be the same. Instead of, if you were going to name it, so if we look here and say there's a double bond there, that looks awful. Say there's a double bond there. Again, we count 1, 2, 3, 4. And we know that there are 4. So it's going to be our butene. because there's a double bond. And where does a double bond start? It starts at 2. So it's 2-butene. This 2 indicates that double bond starts at 2 and goes to 3. And ene tells us that there is a double bond. Practicing is the best way to get the nomenclature down. Practicing is the best way to learn anything, honestly. Now, alkenes and alkynes are also nonpolar compounds. They also only have London dispersion forces. And so they have similar physical properties to alkanes with the same carbon skeletons. And alkenes and alkynes are also insoluble in water, but they're soluble in one another and in nonpolar organic liquids. Alkenes and alkynes that are liquid or solid at room temperature have low densities, less than 1. So they will float on water. So here are some reactions that happen with alkenes. You have addition reactions, which these are all addition reactions to alkenes. And we use these addition reactions to create many important substances that we use regularly. We're going to be talking about polymerization later, and that has opened up a wide variety of products to us. So here, whenever you're adding something to an alkene, it will break the double bond and make it a single bond, and then bond whatever this is to those 2 double bonded carbons. So if we have water and we're adding water to an alkene, we split the water molecules up in its hydrogen and a hydroxyl group, just like, or not a hydroxyl, and a hydroxide group, just like it does in solution itself. It creates the hydrogen ions and the hydroxide ions. Bromine, break that double bond, and it goes on either side of the carbons. Hydrogens, break that double bond, and each carbon gets bonded to a hydrogen. Now, most alkene addition reactions are exothermic, so most release heat. And the products are actually more stable than the reactants because it's lower in energy. Now, just because it's exothermic, remember, it doesn't mean that it's going to be rapid. The rate still depends on the activation energy. And most of them actually require a catalyst to reduce that activation energy to make them go forward. We're going to stop there. That was a lot that we've learned. And we'll do more next time. We'll see you then.